But anyway, you hopefully are all here at the simulation deep dive, or at least looking for the simulation deep dive. My name is Aaron Magnan. I actually do a lot of the technical marketing content you see on YouTube and on our Learn channel as well. There's some of the content that I worked on. Today we're going to be going through all simulation. It's simulation theory, simulation setup. I'm going to be exploring all the different types of studies that we have access to. So I'm not going to read through this whole agenda. Okay, so about us and about what we're trying to accomplish today, and with our Fusion 360 adoption team, we're here to connect everyone out there with product experts to our commercial customers, and essentially, I mean, we're really just there to help you. It's what it is. We are here to help you, to show you how to sculpt, how to simulate, how to do everything that you can inside of Fusion 360. My background is I'm a mechanical engineer. I went to the University of Nevada, Reno. I'm all over LinkedIn. I'm on Twitter. In the past, I was actually a simulation-specific application engineer. So I do have some background in this field, and hopefully what I tell you is valuable because of that. I do also like to make sure that everyone knows how to use the GoToWebinar interface. As you might have known, you can switch to telephone if your audio is not working very well using the computer audio. You can also submit questions, and I do have Marty online with me. She can help out with questions, but I will be pausing every once in a while to address questions and to help you out there. To pose a question, just get in that questions dialogue, or there's even a chat as well. I can see some of you have raised your hands, and as time permits, I'll pause and I'll go and I'll address those. So sorry if there's something that's very pressing at this moment. Again, to get the training files, download the FZ. What kind of file is that? F3Z file that I saved to our Dropbox. You'll then be able to open your data panel, create a project. After opening the project, you can upload the files and drop those downloaded files into it. And the one file that I gave you actually includes a number of smaller other files that we'll be working on. It was just my way of packaging everything together for you guys to get easily. So today's goal, simulation deep dive, we're going to learn all about theory, setup, problems, and common issues and concerns and troubleshooting. So let's jump right into the theory. What we are doing in Fusion simulation is finite element analysis. This is a method, computerized method to analyze designs for things like stress, strain, displacement. Essentially, we're just trying to test your models virtually so you don't have to create quite as many maybe physical prototypes. The way finite element analysis works is it breaks your model into small parts, and we will be getting into that in more detail a little bit later, but that's what the finite element part of FEA stands for. So the last time I did this was probably a while ago, but at the time we only had 4 different study types that we had access to. Today that has essentially doubled with the advanced study types. And you can see this is just a GIF that I threw into this slide that kind of scrolls through the different types that we have access to. We're not going to be covering every one of these. That is just not feasible for the amount of time that we have. I'm going to be focusing on static analyses, which are really the most common that you'll probably use. We will also be looking at some advanced study types as well, and talking about when to use them and why you'd want to consider using them as well. At this point, actually, it's probably a good time for me to run a poll. First of all, I just want to gauge, what kind of experience you have with finite element analysis. If you could just answer the question, let us know if you've, used other tools, or if you're brand new to this functionality. It's going to help me kind of gauge how quickly I might go over certain items. So, looks like just about everyone has replied already. It looks like the majority is actually totally new to FEA, and that's totally cool. That is something that I was anticipating. That's typically the case. It sounds like some of you have used other tools, and some of you are currently using Fusion simulation already, so that's great news. The other poll that I actually really wanted to get into right now was, do you want to cover those advanced analyses types? Because there are two different levels of Fusion 360. It's possible that some of you out there will not be able to follow along if we do some of the advanced study types. That's the one drawback to this. It looks like the majority, again, are saying that you do want to see some of the advanced study types, so I am going to definitely put some emphasis there. If you're not able to follow along, if you don't want to use cloud credits to solve, you can watch as I show you, and it might open up some different ideas for you and how you might want to analyze your products going forward. So thanks everyone for participating in the polls. I'll go ahead and close that, and you guys should be seeing my endless running GIF. Okay, so at that point, let's talk about the user interface and preferences real quick. To do this, I'm actually going to jump into Fusion. Looks like all my files have uploaded. That's what I like to see. I'll close this, and you can see that it hasn't quite refreshed yet. I can hit refresh, and we'll start to see the files in there. Beautiful. Okay, I'm going to pause for just a moment to see if there are some questions or if there's hand raised or any hands raised. Okay, it looks like we're good for the most part. Mostly questions related to sound feedback. Okay, so the user interface for simulation is pretty simple to get into and to start using. I mean, it essentially is built, it is, I should say, built into Fusion, and it's accessed just like you'd access any other workspace. So let's go ahead and just open up a file here. The first file that we're going to be working on is this one original. So if you see that in your data panel, go ahead and double click on it. I love this file. It's from this GrabCAD competition. It was all about this bracket that I think was, put on a wing somewhere, and there's a lot of room for improving it using additive manufacturing, and the results of that were pretty spectacular, to say the least. Anyway, with that file open, I'll go ahead and minimize my data panel for now just by hitting the X there, and I'll just kind of rotate around, and you can see I put GrabCAD on the back of it. That's part of the lesson that we're going to be working on. And right now, there's no, we're not in the simulation workspace. So to access it, again, just use the drop down under Model, and you'll see all the different workspaces we have access to. We'll select Simulation here, and there you go. You can see there is a study that I've built. It's not quite run yet. There's a little warning there. That's okay. We'll come back and address that later. At the top of the screen, you'll see all the ways that you can interact with your models within the simulation workspace, such as creating new studies, applying materials, applying constraints, loads, contexts, etc. And as you get over to the right end here, you're getting into solve, managing, and post-processing. Very important part of the simulation process. Okay, so with that, discussed, let's jump into the preferences as well. This is something that I'm going to suggest that you change just for this course's sake. You can always change it back later at the end, but I'm going to jump into preferences because I'm going to be using a lot of like pounds and inches and things like that. So it's just going to be easier for you to follow along if you are using the same kind of unit system that I'm going to be using. So before I get into the units that I'm really going to be changing here, there's a couple different areas you can go to adjust simulation settings. Here you can see the way that it's going to solve, some of the details behind that. Honestly, I don't know the full details of what we're looking at here. It makes sense, whether or not you're going to say you wanted to use more processors or not. I'm not going to make any changes there. When in doubt, don't make changes. That's my recommendation for everyone using any type of software. I'm going to jump into the unit and value display. Here, you might want to make changes. I'm not a big fan of scientific notation. I'm not going to change it in this case, but you're welcome to change that here. You can hide trailing zeros, helps make it a little bit cleaner. These settings that you're seeing should be all default. But as I get into the simulation default units, this is where I will make a couple little changes. I like to essentially start from like the English style and make a couple little additional changes. I like length in inches. I like mass in pounds. I like force in pounds force, KSI for pressure, and a couple other changes here. Honestly, we're really going to just be using forces mostly, but make any changes you see necessary here. It's up to you. Again, one thing I definitely recommend is using degrees instead of radians. I don't even understand radians anymore. I forget how that stuff works. Okay, so with that determined, let's jump back into the slide and continue on our path here. So our first problem that we're going to be starting is, as I mentioned, related to that GrabCAD study, and we're going to be using a static stress analysis. And so when you're using this type of analysis, it's important to consider some of the assumptions that go along with this type of study. We're assuming that the material is linear, and if that doesn't make sense right now, don't worry, there's another slide that's going to cover that. We're assuming that loads are applied slowly and steadily. In effect, what we're saying there is that we're ignoring inertial effects. Like if you hit something and it, oscillates until it dampens out, we're not accounting for that with the static stress study. We are applying these loads very, very slowly so that those things can be ignored and so that the problem can be solved much faster and easier than the problem that would solve for something like that. We're also assuming that structural deformations are small. So what do we mean by linear materials? There's not really any materials that I would imagine behave linearly across all, stress and strain curves, right? What we're looking at here is a stress strain curve for most ductile materials, your steels, your alloys, metals in general. What happens there is the very first part of the curve is what your elastic modulus is drawn from, or your Young's modulus, if you will. And at some point, it hits a yield and it starts to behave in different ways. So what we're assuming is that any of these problems that we do with this linear static stress strain solver is that we're only considering what happens within this range. And most of the things you design will probably not go beyond that. If it goes beyond that, you probably have bigger concerns, or you might want to reconsider the way that you're doing your design. The reason why we're using that and considering that is that if we do go beyond yield, if your factor of safety goes below 1 essentially, the software will assume that the material continues to behave at that same curve essentially with that Young's modulus. So there's going to be significant error that happens after that point. So this is what we're talking about when we're talking about linear materials. Things like plastics and rubbers and glasses, they perform in different ways. Their stress strain curves look different. Here you can see the carbon steel showing there. Rubber is, or hyperelastics will behave much differently. So if you're designing with something like that, is that something that you can't run with this tool? No, that's not the case. I mean, I actually will use static stress or linear static analyses to solve a lot of different materials, because you can still gain a lot of information about how something is behaving or where high stresses might be in your design. And from there, you can make design changes, maybe bump up a fillet or strengthen something. You can still gain valuable information even if your material doesn't behave in a linear fashion. So something to be aware of. Here is one of the loading. There's actually 4 different loading conditions that goes along with this model. And here are some of the background information, I should say, behind this study that we're going to be creating. So this is a titanium alloy that we're going to be working with. The surface temperature we're actually going to kind of ignore for the analysis' sake. There were some limitations put on by GrabCAD as well for this competition, because this was intended to be created with an additive manufacturing process. So there were some minimum wall thicknesses. We're going to be actually doing some optimization, some shape optimizations on this a little bit later, but there is one interface where there's the load is being applied, obviously where those cylindrical faces are in the center of this part, and the loading condition that we're going to be considering in this first analysis that we're setting up is a vertical load acting upward from that location. Okay, and the original model looks like this. If you go to GrabCAD, you can look this up as well. It was some General Electric aviation bracket, something or other. But the process that we're going to go through, and I've made a couple little modifications to this model to help present these different ideas and to walk through how you would approach a real analysis with a real model that you've designed, is we're going to start with some model simplification. So that text that I showed you that was on the back of that, I mean, that doesn't add a lot for the analysis, right? It doesn't strengthen the model. It doesn't weaken the model significantly either. What it does do, though, is that it causes the mesh, the way that you're breaking down this complex shape into these finite elements, it makes that mesh overly complex, and actually it can cause errors. And that error message that you saw in the Fusion interface on that model is actually indicating just that. It was an error related to trying to solve with some of these complex features that are on this model to start. From there, we're going to go and we're going to verify that the material has been defined. We're going to show you how to change materials, and we're going to look at constraints and loads, aka boundary conditions, some people call it that. And we're going to use a couple of different structural constraints. Again, it's just not possible for us to talk about all the different options within this tool in the time frame that we're allotted here, but we're going to try to talk about most of them and provide some information. So let's go ahead and get up to that point. So I don't want to present the whole setup and run through it all in one quick go. This is intended for you to follow along. So to start off, what we're going to do is we're actually going to begin a brand new study. There is one that exists there, but don't worry about that. We're going to select a new simulation study, or as you can see, I can hit N on my keyboard to actually use a keyboard shortcut to get there. When we get there, your study selection might look like this. If there are blank spots in your study selection, let me know. That's a little issue that we've been dealing with, and actually I do have a workaround to present, and I'll probably show it either way just to make sure. But I'm going to select to do a static stress analysis. If you wanted to get into settings right off the get-go, you could expand these out and kind of dig into this, but all I really want to do here is just say start study, or I give it a name so that I have some organization built into these study names. In addition, we can look at information related to the mesh. We can look at adaptive mesh refinement options, and I'm going to turn off the automatic refinement control to begin with, and I'm going to jump into the mesh as well, and I might see if I can turn off this curved mesh elements. I'll be talking a lot about mesh as a part of a later lesson. What I'll tell you right now about that curved mesh elements is that by deselecting that, it reduces the quality of your solve, but it's going to enable us to run these very quickly and very easily as well. So I'm going to clear that option and click OK, and once we do so, we should see a Start Study option here. If your appearance changed, like if it changed from what might have looked like steel to like a darker gray, that's because you might have your study material showing. So whatever study material you define within this analysis will start to show within the interface if you have this shown as I have it set right now. I like to usually have this off, to be honest, because I don't like, if I've built in color and appearances to an assembly and I'm using that to like visualize parts and apply constraints and loads a little bit easier, I like to just maintain that same painted color. I don't really care to see the study material color showing through in the analysis interface. That was very long-winded. Okay, so let's continue on, and essentially, when you're creating a simulation inside of Fusion 360, you're going to start from the top and work your way down. This is the best way to approach this because there are some things that kind of depend on the setting before it. Like, for instance, you don't want to mesh until you've defined things like contact, and you know, you can't run until you've defined everything else. So that's why, you know, results and run is kind of at the bottom. It's presented in somewhat of a chronological order. So the first folder that you see here, I'll expand out, and essentially what you're seeing here is a breakdown of all the different bodies in this analysis. This is a boring one because there's only one single body here. We're doing a single part analysis. So right off the bat, I mean, if I wanted to ignore certain parts, I could clear the checkbox here. We're going to be doing that with a later analysis when we're actually getting into an assembly. But for now, we're just going to keep it as is. Obviously, we want to run the analysis on the body that's showing. That's the only body that we have in here. So good to know what that first folder is for, but in this case, it doesn't provide us a lot of insight. From there, we can get into study materials. And as I mentioned, this is a titanium alloy that we're actually looking to use, but the way it was brought into Fusion, it was by default created with steel maybe, or that's the default material setting that I have within my preferences. So this isn't quite representing what I want it to. So what I can do here is I can right click on my study materials and get into things like material properties, manage physical materials, or study materials. I'll select the first one here. We'll get into the other ones a little bit later, but here you can see it's showing me all the different bodies in this analysis, aka one single body, and here we can define the study material to differ from what it might have been designed with. So I'll use the drop down here, and you can see a nice little list of materials that we have access to. Any of the ones that have the warning are telling you it's probably not a good material choice for this type of study, or there might be information missing in order to solve this. Things like woods are very, very hard to analyze with finite element analysis because they react differently in different loading directions. And there's defects, there's knots, and there's all kinds of things that can happen with things like that. So would I use finite element analysis to analyze something that's designed with wood? Probably not, but like I said before, you can still learn about where weaknesses might be present in the model. To find my titanium, I'm going to hit T on my keyboard, and it's going to kind of filter down to the T section here, and you can see there's a couple different titanium options. We actually have the one that was mentioned in that study, so that's great to use, and I'll select that. And you can select your safety factor, how it's actually going to be determined. In most all cases, you're going to be using yield strength, so we'll go ahead and use that, or keep it as is, I should say. And I'll click OK. So now at this point, with the material property differing from the design, you can see as I turn it on or off, there's a very slight color change. The reason why I usually have this actually off, like I said, is just to visualize things better, and it's usually because I've applied appearances to models. Okay, so we'll continue on to define our boundary conditions. So boundary conditions will describe how the model is constrained or how it's loaded. Now, I forgot a step, right? The first thing I wanted to do here was I wanted to actually simplify the model. And what helped me realize that I forgot a step is that I still see threads within these holes. And threads are great to model in some cases. I mean, if you want to make something look great, but they're not great for performance of simulations. They're not great for performance of large assemblies either. So that's something I want to fix. And obviously the grab cat on the back I want to get rid of. So let's go ahead and do that now. I'm going to use the drop down to change back to my modeling workspace. And I'm going to get rid of the text on the back, the deboss text on the back, using our direct editing methods. This was an imported model, so automatically I'm in a direct editing mode. I'm not capturing design history. This makes things like what I'm going to do right now much easier. But with my selections set to select through, I'm going to just kind of rotate the model till I'm looking at it from the top. And I'm going to do a Windows selection. Let's see what I get when I do this. And looks like I got all the text that I was looking for. That select through ensures that I get everything, even though it was hidden from the view I was looking at before. And I'll just hit delete on my keyboard, and that's going to delete that out of there. The threads could be dealt with in a similar manner, but you can also just, right click them from the tree. I actually added these after the fact because I wanted to build in a simplification and talk to you why that's important. So here I'm going to just delete these guys out, just right click and delete, and I'm just going to do these one at a time. Okay, so we're checking all the boxes. Doing things out of order is something that happens, right? You forget something, you need to go back and change it. It's very easy with the way that Fusion has it set up, because we can very easily switch back to simulation, back to modeling, etc., without really losing anything. So we'll switch back to our simulation workspace, and nothing's changed here. That doesn't mean to say that if you were to do that at a later time with different phases, it wouldn't cause any issues, because if I had a contact, or if I had a load applied to like the threaded face, if you delete that out, obviously it's gonna be missing that reference. So something to consider. It's usually better to do your model simplification before you start creating your simulation studies. Okay, so at this point, let's define some information about the loading condition. So I will expand out my loading case 1 here, and you can see there's things like loads and constraints, and these go along with what you see at the top of the screen here. Your constraints include things like structural constraints, which we'll be using. Bolt connectors, we'll be showing you those a little bit later. Rigid body connectors, and your loads include all kinds of things like gravity, point masses, angular loads, structural loads, etc. Okay, so I'm actually going to access these using some keyboard shortcuts. I love using keyboard shortcuts. If you read my blogs, you know that I really like being efficient. So I'm going to hit C, and we're going to start defining constraints to begin with. And we're going to actually fix the locations where the bolt holes are located. We could use a bolted connector and thread the use like a threaded definition, but for this first case, I want to keep it simple, so we're going to use a fixed style constraint. So what this does is it ties this model down into this simulation, for this simulation's sake, I should say. So one thing about any finite element analysis is that as you create something, it will have 6 degrees of freedom. It can translate in 3 directions, X, Y, Z, and it can rotate about each one of those axes as well. So we need to constrain this model so that it's not going to fly off the screen if we apply a load to it. So we're going to go ahead and apply this fixture to the 4 faces here, here, and here. And you do have some say over how it's actually constraining these. I could clear one of these boxes if I wanted to. I could change it to a different style contact, or constraint I should say. But fix is what we're looking for, so no need to overcomplicate things. Let's go ahead and click OK. We'll flip around to the back end here, and I want to apply another constraint as well, because this is actually, while those are bolted, there's actually like a wing or some other part of the aircraft that's on the other side of this that's going to resist any movement in that direction. So I'm going to hit C again, and it's going to enable me to create another constraint. And in this case, I want to actually make a frictionless style. So it's going to be free to slide about the face that we select. So we'll select the bottom face of this model, frictionless. That's it. We're well on our way to defining the constraints for this. Click OK, and just like that, you can see there's a couple icons here. This represents frictionless, obviously, and the little lock is representing your fixtures, your fixed style constraint. If you don't like to see those, by the way, you can very easily hide all of them using the option there, or you can expand this out and hide individual ones. A lot of times I like to hide them. I'm more interested in seeing, load representations within this interface. So it's up to you how you want to do this. I'm going to go ahead and hide these, as mentioned, just to help clear up the user interface a little bit. Okay, and from here, the next thing I want to do is I want to create a load. So this is usually the easiest thing for people to do. I mean, constraints takes a little bit of additional thought as to, how the model's connected to maybe the next model that it's really, attached to. But loads, people typically have a very good, clear understanding of, how they're being applied. I mean, obviously, if you're going to create a simulation, you do have some idea of how things are loaded. So I'm going to hit L on my keyboard. That's another keyboard shortcut for you. And loads can be things like, forces, pressures, hydrostatic pressures, which will change with depth, bearing loads, remote forces. So, the reason why we only have a single part showing here rather than, modeling the wing and the pin is simulations take time to solve. And so the simpler you can make them, the better. Remote forces and remote loads enable you to apply forces off at a distance, even if you don't want to actually include the model that might be actually having the force applied to it. So we'll select force in the end there after my babbling, and we will select the two cylindrical faces, and we'll rotate around. And do you notice how this is very difficult to rotate right now? This is annoying me, so I want to address this right now. I like to use the constrained orbit style. The weird thing about this model is that it is oriented in a very weird way. It's like oriented, I don't know. If you look at the front, this is the front orientation, which I don't really believe is to be the front. So to help me rotate this easier, I'm going to show you a little secret. Not a secret, but something I've showed in quick tips before. I'm going to rotate the view to this top corner here because this is, for the sake of this analysis, it's looking at it in the way that I would consider to be the top. I will right click the home here and I will set the current view as the top. This is going to make it so much easier for me to rotate around this model and actually get the view that I want. So, the way that this thing is positioned on the next component, this is how I'd like to analyze or rotate it. So real quick way to adjust the view. The problem is that the default view orientation has that weird layout, so we just need to adjust it. This is an imported model, obviously, right? So that's why that happened in this case. Okay. So with that, the main reason why I did that is so I could look at this from the side and I could show you how to apply this force in the vertical direction as indicated in the setup for this problem. So one thing that I want you to pay particular attention to is, how we're applying this force. Is this force going to be per entity? Because the total force in this case should be 8,000. So if I use this option to do a force per entity, I need to split that in two, right? Because I have two items selected. If we clear that and say 8,000 pounds, it's going to essentially do the same thing. Now, if you have varying forces and loads being applied to multiple different faces, I would recommend that you do those all as individual structural loads. The reason for that is, and I'm going to go a little bit off track here, but you can keep your selection as is. If I'm applying two forces to, say, this face and this face, how does it distribute the 8,000 pound force load? Well, what it does is it actually looks and distributes it per size. So because this face is larger than this face, it's going to get more of that 8,000 pound load. So in order to avoid any of that confusion that can be caused by this distribution of overall force, I'd recommend that you do them as individual loads. Back to this, however, we're going to set this as 8,000 pounds. And we have very easy ways of manipulating, direction and things like that. We want this to go up, and I can kind of try to eyeball it until I get it up, pointing upward. But, I'm not really certain if that's going directly upward. That's not really the way I want to define this. So instead, I'm going to select this reference option, and I'm going to select the vertical edge. So I'll select the edge that you see here. Now that's ensuring that the way that we're applying this load is acting directly upward along with this edge that we used as a reference. Now we can continue to still rotate if we'd like, but that's exactly the direction I want to apply this. So we're good. We'll go ahead and click OK. we have the force, we have the constraints, and so on. I think I'm going to jump back to the PowerPoint for a quick second here. Next things up include setup related to contacts, setup related to mesh, and setup related to solve and post-processing. So, and I don't even know why I jumped back into the slideshow to show you that. I could have told you that just as easily. So, at this point, we want to talk about contacts. Now, the only time contacts really come into play is if you have a model with multiple parts or multiple components, multiple bodies interacting with one another. In this case, we don't need to address contacts, obviously. There's nothing that this part is contacting to and no other parts. Fusion simulation will not consider your joints. It will not consider any of that information that you might build into the actual assembly design. You need to define contacts and constraints and things like that within this context. So that said, we don't need to address that. The next thing we can get into is creating the mesh. So if I'd like to, I can right click on the mesh folder here and I can select to get into mesh settings. You saw me change those earlier when I actually jumped into the settings as we created the study. We can toggle mesh visibility, but we haven't actually calculated the mesh yet. Or we can generate mesh. I'm going to select to generate the mesh, and this is going to do, as I mentioned before, it's going to break this down into these finite elements that we were talking about before. So the element types that we have within Fusion 360 are tetrahedrons. Tetrahedrals. It's triangular on all sides. It's a very commonly used element shape. So Marty's telling me I'm cutting out a lot. I apologize once again. All I was saying there is that within Fusion simulation, the element type that you have is this tetrahedral. It's triangular on all sides, although you're really only seeing the top surface of this triangle. It actually goes within this model. This is a pretty coarse mesh, and as I showed you in the setup, I did that to help me get through these studies faster for this first case. And as a result, the results can be affected by that, and that's something I'm going to be showing you. So at this point, we can go ahead and solve. We've defined material, we've defined loads, we've defined constraints. We could skip contact, and so let's go ahead and do it. I'm going to click the solve button from the toolbar, and we can solve this locally. It will solve very fast. I'm going to select this study, start study, the one that I created during this, and I'm going to click solve. This should solve very fast, depending on everyone's machines, I guess, out there. When you do solve locally, obviously you're kind of locked out. You can't really go do anything else. So hopefully everyone's will solve in a similar amount of time that mine solved. But just like that, you should start to see your results, and you should start to see what's going on with this model. So the first result type that you're seeing here is showing me displacement. Okay, so with this displacement plot that we're seeing right now, what I want you to note is that the amount of displacement that you're seeing here can look very accentuated. It can be made to look much worse than it actually is. So right off the bat, let's talk about that, and let's see how we can adjust that to make it either look, more realistic or to accentuate it even more so. So I'll use the drop down under results to get into deformation scale. As you can see, the default here that it's using currently is adjusted. So although the actual displacement here is 0.003 inches essentially, what you're actually seeing on screen is accentuated to help us visualize that. The way that it determines the value here is some internal algorithm. It usually does a very good job of presenting the displacement in such a way that we can see it better. However, in some cases, you want it to show actual displacement. When I change it to that, you can see how far those pieces move. If we wanted to deform it even more so, we could bump it up to 5 times. And this is where that poor quality mesh really starts to shine through and through. But at this point, you can see this displacement is very accentuated. It looks very bad, to be totally honest. So I'm going to change that back to adjusted, and that's going to do a good job of letting us visualize what's happening there. Now we have additional results available to us, obviously, in lots of different ways of post-processing this. But before I get into that, I want to create some additional studies. I want to run this a couple more times and maybe adjust the mesh, maybe adjust some other details behind it. And we're going to solve those hopefully while we're actually post-processing some of the results on this one. So we'll come back to post-processing this guy in just a moment here. What I want to do at this point is I want to right-click the top level name, the study name from our browser, and I'm going to select to clone it. I've cloned this, and you can see it doesn't have any results related to it. I'd have to resolve it to see those results. You can see the one before it does still have results, and I can see which one is active by the coloration in the browser. So start study in 2, the one I just cloned, is the one that we're looking at right now. There's no results. I can slow left click on the name from the browser if I want to rename this, and maybe I'll say mesh control or mesh adjustment, because that's what we're actually going to be doing here. So with this one, I want to right click on the mesh, and I want to go back to those mesh settings, and let's turn the curved elements back on, and we'll click OK, and we'll go ahead and we'll actually, before I actually solve it again, I want to clone it another time. So I'm going to clone it again, and I'm going to call this one mesh control 2, and actually this time I'm going to apply some real localized mesh controls to this study. So this one copied the curve style elements from the previous study because I cloned the changes that I had made. So in this case, I want to adjust the mesh slightly more, and I want to increase the mesh density in the areas where the highest stresses are, or where the highest displacements might be. So to do that, I'm going to use the drop down under manage, and I'm going to select local mesh control. This is relatively new to Fusion 360, but it's very important because, like I say, when you're running these things, when you're running simulations, very oftentimes you want to balance quality with solve time, because if you make everything infinitely small, if you make those elements infinitely small, your simulations will take a very long time to run. I mean, the results will be potentially better, but it's diminishing. There are diminishing returns on mesh refinements that you do. So that said, adjusting meshes globally, it doesn't always do the trick. Sometimes you have to use localized mesh controls. And so in this case, I'm going to apply these mesh controls maybe to the fillets there and the flat faces here. You're welcome to use different settings or select different faces if you'd like. Anything that you saw that you'd like to refine, feel free to select in this case. We can refine by face or edge selection. We can also do it for entire bodies if we'd like. So if you're working on an assembly with 20 parts, you have a small part in there you want to analyze very detailed, you can do it by body as well. So with that selected, I'm going to now grab this slider, and I'm going to select to make those faces finer than they were before. Now, don't get too crazy with this. I'm going to just slide this over to the left a couple spots and click OK, and there we go. We've adjusted the mesh in just those very localized areas. Okay, so with that created, you will now find a new folder within your browser that's showing you those local mesh controls. So good to know, good to access, good to be able to go back and recall and edit if you need to at a later time. So at this point, I have 2 additional studies I want to run. I'm going to go ahead and select the solve button once again. And in this case, I'm going to use the on cloud option, and you don't need to do this necessarily. I don't want to be costing you cloud credits, but I'm going to use on cloud. I'm going to select these 2 guys, and if you're solving them one at a time locally, go ahead and start those and start watching what I'm going to be doing next. I'm going to click the solve button. The beauty of the cloud solve is that I can close this solver window and I can go work on other things. So as I mentioned before, I can go and I can double click on the start study and start, or continue, I should say, post-processing these results. So these guys are running in the background. If you need to access the solve that's happening, you can always do so. You can select the item that you see here, the solve status, and you can see they're still chugging away there, and at some point they'll be coming back to us with those results. Okay, so to continue post-processing this, let's look at some of the ways that we can do this. Displacement's, one area of interest for studies of this type. Stress is another one. This is reported to me in KSI. Typically, you're only interested in like the highest areas of stress, so I can actually use the slider here from the scale, and if you move your cursor over it and left click and hold, you'll be able to drag it to kind of filter through to just see the results at one end of the spectrum or the other. The other thing that you can do here is that you can adjust the scale altogether, and this is not very discoverable. It probably took me 2 months to find it, or longer. I just don't want to admit how long it actually took me. But if you double click on the scale here, you can access the ability to change this manually. So instead of using the global max and min, which Fusion will do by default, I could say maybe I just want to see where it's 20 KSI, or I want it to be fully colored red for that 20 KSI range. So using this, you can visualize these models in different ways. Again, if you get too crazy with it, your results are going to start to become less and less valuable to you. So, something like 30 might be good. You can see a little more red coloration in the results there, and we like the looks of that. Looks like one of my studies finished. Mesh Control 2 came back. We'll go ahead and start looking at that in a little bit. But here you can see, the stress in this looks like the max is 40 KSI. If we switch to safety factor, the minimum in this case is 3.2. And for aeronautical designs, that's a little bit of overkill. I think typically they'd be looking for like a safety factor of 2, and that GrabCAD study probably had information pertaining to how how optimized you could actually make it. Obviously, you don't want these things failing at any time. Okay, so that constraint over thing is really bothering me. Hopefully you're having better luck. I can always use the triad or the view cube as well, so that helps. Okay, so these results, they're okay. Really bad quality, however. If we go and we double click on the mesh control option here, we're starting to see more refined results. And I mean, right away, you can see the shape of this circle actually kind of starts to look more like a circle again. That's because there's more elements in there. That's because we're using that curved style element, which introduces more detail, essentially. If we look at stress, the stress might be higher in this case. That's because your mesh, as your mesh gets smaller, you get more details in areas where there might be very high stress concentrations. So there will be some slight differences here, but there's ways that you can verify that your results have converged. We'll talk about that in a little bit. So the real thing I wanted to show you here was the mesh for this model. If I click to show the mesh using the option in the browser here, I'm just clicking on and off so you guys can see where it is. We can visualize and compare maybe the mesh between this and the start study and say the last study. So I'm going to turn on the mesh here, and again, to activate the different studies, just double click and that'll turn it on. And you can see it looks like that's a little bit finer in Mesh Control 2 than the first Mesh Control option that we created. Okay, so who likes double clicking on each study to visualize and try to compare results? I certainly don't. Luckily, we have a tool within Fusion 360 that enables us to compare our simulation results very quickly, very easily, and side by side. So it's actually accessed from a different workspace. I'm going to use the drop-down under Simulation to change to my Compare dialog. My Compare workspace, I should say. So you can see there's two different models showing now. We can use different layouts here if I want to see all three of these at once, or four if you can fit as many in here as you can try, but I might just go with three in this case. I mean, that's obviously how many studies we have. What's neat is that as I zoom in on one, it's going to zoom in on both, and it's synchronizing that using the options found up here to synchronize the camera. I would definitely recommend that you use that at all times, and again, that's the default. But right now, it looks like I'm looking at mesh control for this one. I'm looking at mesh control for this one, and same for the third. So we're not really comparing anything right now. So let's make some changes here. Let's change this to maybe the start study, the one with the really bad mesh. Let's change this guy. And to make changes to them, you just need to click within the area of the workspace to activate it essentially. And then from there, you can see this little drop down where you can change it to mesh control 2. So mesh control 2, and start study. So these results all look fairly similar. I mean, the displacements are not significantly different between each one of these. A little bit different between the first one, but again, as mentioned, that quality is pretty poor in that case. What we can do here to kind of compare these different results side by side is we can synchronize result types. So if I want to go and look at stress now, here we might start to see some differences, right? So it's like, 40,000 or 40 KSI, 40.1 KSI, 39.7 KSI. So there's some differences there. And this is tied to the way that we're solving these. We're breaking these down into these little elements, and those elements can definitely play into your results. But we're not seeing any real significant differences there. I'm going to turn on the meshes in each one of these. So I'm going to select each window and select to hide or show the mesh. And this is where we can really get into comparing the meshes in these cases. So having these three guys side by side, you can definitely see which one has the best mesh. It looks like mesh control 2, which one has the worst mesh, and which one has kind of the mid-grade mesh. Okay, so at this point, let's look at safety factor once again, and we can see, and it was kind of hard to see this. Safety factors are all pretty close. That's directly related to that stress value that we were seeing before. Okay, so let's go ahead and move back to the simulation workspace, and let's see how we can really verify this once again. And I'm going to use the start study in this case to do it, just because it has that really coarse mesh and we'll be able to solve this very fast. So what I want to do here is I want to right click on mesh, and I want to get into my mesh settings. Actually, no, I lied. I want to get into my settings, my overall study settings, which are accessed from this button that you see here. And we're going to turn on our adaptive refinement controls, and we're going to set this to the highest level. We're going to click OK, and we are going to solve it once again. And I'm going to do this one locally, so if you are following along, it hopefully will be done very quickly because of that very poor quality that we're looking at. What that adaptive mesh refinement tool will do, and I apologize if I did that very fast. I'm realizing I did that very fast, but if anyone has questions, we're approaching our first break here in just a moment. But what that will do is it will solve numerous times, up to 6 different times if you saw the dialogue that we were in as I defined it. And what it will do is it will refine the mesh between each solve. And you can see at the end of this, it's actually refined the mesh pretty dramatically in the areas where the highest stresses are, where you're really most concerned with looking at these results. I'm going to switch to my stress results and kind of visualize this a little bit more. So to understand what it was doing there in even more detail, we can select this guy, this convergence plot. This is one of our result options that we have access to. I'm going to select it, and what it's reporting to us is the stress over each run. So as you refine the mesh, you typically will want to see either the stress converge on a value, and I wouldn't say that the stress really converged very well yet. I mean, you could analyze this and adjust the settings even more to get it to converge even more. But what's more important in the way that we're going to use to verify that our results are of better quality is we're going to look at our displacement convergence plot. Typically, your displacement plots will always converge, and whether you have what are called singularities, and there's a quick tip related to that, which I'd recommend everyone see after this video. And it has to do with the way that the mathematics is actually solved. So the way these are solved, and I'm not going to pretend like I remember all this. I'm many years out of school, but the way these solve is it solves for displacement. It takes the integral and it solves then for stress, and in doing so, there's some mathematical issues that can occur, singularities being one of those. The reason why we look at displacement is that if it converges, then typically your stress results will have converged as well. I should say you can then treat your stress results as if they converge, because even if there is a singularity and it causes it to diverge, then your results will still be valid, and this is one way to verify that. Okay, I think I almost need a break, right? I've been talking for a very long time, and I'm having trouble finding the right words. Anyway, I'm going to recommend that in the next 5 minutes when we're taking our break that you guys either dig down into more of the result options that you have. I mean, I was just looking at some of the options available to you. I mean, if you look at your displacement, you can do it either for like the magnitude, or you can look at displacement in particular directions. If you're just interested in displacement in a particular direction, you can use X, Y, or Z coordinates to determine that. You can look at stresses in all kinds of different ways. There's contact pressures if there's multiple, and basically this is the workflow you go through when you're analyzing something. You simplify, you apply materials, you define your constraints, you solve, you analyze, you make maybe a design change, and you repeat this process. And the more you do this, the higher quality your designs will be, and the less physical prototyping you'll have to do. Doing virtual prototypes will save your companies all kinds of time and money. It's going to ensure that your designs are very well vetted and optimized. So if you want, you can either continue on with some of the other analyses for this model. You can make some design changes, maybe remove some material to try to get that factor of safety closer to 2. You could try to set it up with the different load analyses that go along with this. Or I've also included these 2 models. These were actually submitted for that GrabCAD competition. If you want to look at these and try to figure out which one was better, you can. Considering it's only 5 minutes, that might be something you do later on, but definitely something that's kind of fun to play with and a good test of your skills. So I'm going to keep this on screen as we take a little break. Okay, so with the 5 minutes that I gave you, hopefully you guys all got through all those different loading conditions. Like I say, you should have access to this slideshow. Go ahead and try this out later if you want to give it a shot. It is a finish challenge, so your results will not really matter, but it's a good exercise to run through. Okay, continue on. We're going to be looking at some different considerations, and I did take a lot longer with that first setup, so I'm going to be going a little bit faster. I'm going to also be maybe not running all the studies either. I wasn't really planning to do it originally unless I had time, so you're just kind of to take what I say as you can always run them later, but we're going to go ahead and just try to run through as many setups as possible. Before I jump back into Fusion, I did want to note how you can create new materials. There are going to be a lot of times where materials that you're using in the simulation might differ, or materials that you purchase or are using might differ from what are included in the database. To do this, it's a little bit hidden there, but you jump into the material browser, the physical material browser, you click the button down here on the left to add a new, and then you start filling out the details. obviously, to run a simulation, what you see on this first tab is really just about the identity. It doesn't include anything about the simulation. So in order to actually be able to use it in the simulation, you'll have to add additional tabs with information for the physical characteristics. To get custom materials, there are places like MapWeb. You can get material spec sheets. These are all links as well. I hope they actually come through in the PDF that I created. Sorry about that. And there's also vendor information that you can use as well. In this second setup, we're going to be talking in detail about contact, what each contact means, and hopefully that'll help address some of the concerns that people were posing in the questions pane about why I use a frictionless constraint. Because, I mean, if you don't trust or if you don't like that setting, instead of using a frictionless constraint on the bottom of the bracket that I showed in the last case, maybe you could actually, model a part of whatever the next component is. I mean, yeah, it's going to take more time to mesh and solve, but you can potentially get better results. And you could use a different contact there. You could actually use like a separating contact there, and that will be more closely resembling what's happening on the bottom of the bracket. The reason why I use frictionless there is because it's free to slide. I didn't want to fix it, but I didn't also want it to be able to push down into or pull off of the face that was there. So that's why I chose to use frictionless. Again, this is a numerical method. This is a computerized, analysis. It is something that sometimes you do make changes to it, and you do maybe represent things inside of the software that aren't fully representative of what's happening in the real life situation. So there are certain things that you might have to adjust and get into. Okay, so let's jump back into Fusion. I'm going to open up my data panel, and let's go ahead, and there's two options I have here. I have the pipe wrench, or I have this bracket. I'm going to do the bracket because it gives me the opportunity to show you some other things as well. Okay, so this bracket for sim model gives us a way to represent a couple different things inside of Fusion simulation that's valuable to know. So now we're looking at this brand new study, brand new component with multiple bodies now. And you can see there's the bracket part, there's the support that's modeled as a separate body, and then there's the wall as well. So that means we need to start to address things like contact and we can play with how these things are actually connected to one another. So one way we could actually represent this is, the main way that we want to represent how these models interact is using contact. So you can do this manually. You can also define automatic contacts, and typically I will always recommend that you do automatic contacts to start, and then you go and adjust manually, or you add manual contacts at a later time. When I select to do automatic contacts here, there is a certain tolerance that Fusion will use. Good designs will have tolerance gaps built into them. I mean, you won't always know that this bracket will be this certain size. You won't make this support. I mean, in this case, it doesn't really matter because you could just slide it one way or the other. But there's always going to be small gaps in good designs, and this will enable you to overcome that, to create those contacts very, very easily. When I select generate, it finds all the contact in this model, and we'll see what it does from there, and we'll see how to adjust those. So we'll right-click on our on our contacts folder, and now we'll select to manage those contacts. So there are, it looks like 4 different contacts in here, and I can select each one, and it's going to cross-highlight, the faces that it's connecting there. So like the support in the bottom of the bracket, and then it looks like it's getting like this filleted or this bent edge in the plate. It's also getting the back face of the bracket and the plate, and so on and so forth. So in this case, it's using bonded as the contact type for all of these. which isn't necessarily accurate, because the way this is actually connected here, and this kind of goes along with that question I kept getting about frictionless constraint in the other bracket example. The back of this model is not bonded to this face. It's actually free to slide, right? What's actually connecting it are the bolts that go through these holes. So we could actually represent those bolts with things like bolt connectors. So that's what we want to do here, and that's what I'm going to represent, and that's what I'm going to set up. So first of all, in this case, I do want to apply maybe some constraints to kind of tie this thing down and give you guys an idea of how this thing would be set up. So I'm going to hit C on my keyboard, and I can fix the wall, I can fix either all sides of it and maybe even the back of it. I mean, I'm not really concerned with what happens with this wall. What I'm really concerned with analyzing is the bracket itself and maybe the support. So that's very well fixed down. If I select the degree of freedom view right now, it looks like everything is fully constrained, right? That's because the contact is there. The contact is there. It's being treated between all these bodies. The only one that actually truly has fixtures on it or constraints on it is the wall itself. But because everything is connected in this design, everything is fully fixed at this point. If I were to delete the contacts, then you'd start to see things be free or partially free, etc. Or maybe if I change contacts, and that's what I'm going to do just now. So I'm going to right click on my contacts folder, and I'm going to get back into managing contacts. While the list by contact set is sometimes nice if it's a really simple model, list by bodies is about 10,000 times better. So in this case, I'm actually going to use both of the contact sets within the wall or attached to the wall, and I'm going to change them. So by default, when you do the automatic contacts, it's going to make everything bonded. Bonded contacts treat it just like it sounds. It treats those faces as if they have some infinitely strong glue holding them together. It's as if they are one. Not very accurate in this case. So we're going to use this edit option to change this, and instead of bonded, we have a couple different ones we can choose from. We can use sliding, which would enable that face to slide upon it. We could use separation. So depending on if the force that I apply to this is pulling or pushing, it could act differently. It could push into the face, it could pull off the face as well. So we're going to use separation in this case and click OK. There are a lot of other details there as well. Again, it's just not one of those things that we have time for. We're going to set the second one as separation as well, even though that second one that I defined is actually between maybe the rounded edge and the back face. Depending on how the load's acting on this, it might not even come into play. Okay, so that's more accurate in terms of the contact, but if we go and look at the degree of freedom view, all of a sudden now we have this issue where it's not seeing that these bodies are connected in any way. So the one body that has a fixture or constraint applied to it, the wall, is the only thing that's fully fixed in this case. So let's address that, and the way we're going to address that is with those bolts. So we're going to use the drop down on constraint, getting to our bolt connector, and we're going to start to select these different items. So we're going to select the outside edge here as the location where the bolt will be located. We'll select the back face here, and it will not enable you to do that unless they are perfectly aligned. So make sure that any holes that you have, any bolts that you're trying to create, have that consideration built into them. Alternatively, we could actually use a different style here. We could say a threaded hole, and we could say, the nut will be there, or the top of the bolt will be there, and then the location for the threads will be on this face. And so that takes on a different appearance. It also, will affect the results. So we'll keep that as is. One thing that is extremely important when you're defining bolts, and I can't emphasize that enough, extremely, extremely important when you're defining bolts, is that you consider the bolt preload. Bolt preload will affect how these bolts react and how your model reacts, and a lot of different details into how this actually will be represented within the simulation. We can add head washers if we'd like as well, but what I want to do here is I want to make this preload, and I'm just picking a value out of thin air. You do really want to double check and see what to use, and Fastenal actually has information pertaining to that. But there we go. We've added a bolt, and I can go and I can repeat the bolt connector, and I'll select again to do from there. And this time I'll use a with nut option. It'll take on that different appearance. And again, we'll define this bolt preload. We can define the preload in two different ways. We can either use an axial definition, which, typically is not that easy, I think, to get, or you can use like a torque to define this preload, which does some like internal calculations. So, okay, so there we go. We've created those. If we look at the degree of freedom plot, all of a sudden we have that connection once again, and we're actually ready to run this once we have defined, loads and whatever else we need to define here, mesh, etc. I'm not going to be solving this guy. You're welcome to try to solve it on your own time, but that was the main thing I wanted to cover here were the bolt connectors, and I wanted to make sure to cover the contact type. Now, I tried to, like, right before this class started and before Marty interrupted me, I was playing with some different contact examples to help demonstrate how these things will react. So in this case, just to introduce you to the model, there's basically three bodies here. There's the fixed bottom body that we're going to be using, and I'm going to hide these two guys to begin with, which you'll note has a split face, which is important to consider. And actually, I'll use a different model to show you how you can use split faces and how you can apply loads in different ways. We have the next body on it, which is the loaded face, which again has some split faces there to be able to select different things. And then we also have this loaded model with gap. So there's a small gap in there. And the simulations that I've set up here demonstrate each one of these different types of, I gotta show this body, sorry. Make sure to show all three of those. Back to the simulation. This hopefully will help demonstrate what these different contacts will do. So as mentioned, bonded will treat those faces as if they are, essentially the same model. They can still be of different materials, but using this bonded contact will glue them together with this infinitely strong glue that does not really exist in real life. But there are cases where you do definitely want to use bonded. And I should also mention that bonded contact sets actually solve much faster than the alternative types. When you have separation, that makes it much more complex for the mathematics to run. When you have sliding, it's more complex to solve. So something to be aware of and to consider. Sliding will do just like it sounds. With the load acting like it is, it's going to cause this thing to kind of slide off, and the displacement in this case is 461 inches. That's because, with nothing else to constrain that top model, it's just going to fly off the screen. The only reason why I was able to solve this, typically you wouldn't really be able to solve this, is because I turned on a setting here to remove rigid body modes. That just helps me to solve something that might not be really fully accurate or able to solve otherwise. For the separation case, I did it 2 times, and a little background info as to how I did this and why I did this is, and that's why I actually split the back faces there. I needed to bond something because if I pushed on it again, it would just fly off the screen. It wouldn't really do you much good to visualize this. But with separation, even though those faces start together, I'm able to separate those two guys. The areas that were split in the back are bonded. That's why I did that originally. There is another contact style that enables you to bond even though there are gaps. So in this case, I was doing just that. I was using that bonded with gap style. So that's why I created that third body that you saw there. And then this last case was another separation case where, again, I bonded the back faces of these together, but I was pressing down on one side, I was pulling up on the other, and you can see it's, not enabling this to pass through that face, but it's actually able to slide on it a little bit. So, this separation style contact is probably the most accurate way to solve a lot of things and most accurately describes how faces come together. That could help you overcome the questions that you had on how we'd constrain that bracket in the earlier example. So definitely something to be aware of. These do take much longer to solve. You know what? I'm going to stick with this model because will enable me to demonstrate a couple of things. So I'm going to hide this guy. So say I wanted to apply a force, but I only want it to be applied to a very particular area. Maybe, it's a finger pushing on this. It's there's something bonded to it, pulling on it, whatever it might be. The way that fixtures or loads, I should say, are typically applied or adjusted. I'm creating a real quick study here. Hit L on my keyboard to apply it. The way it'll typically do it is it will apply it across the entire face. Even though this is all one single body, I actually split this into two faces, and that enables me to apply, the force to one side or the other. It doesn't change anything about the geometry. It doesn't change anything about how it reacts. It really just changes how you apply the loads, and this will enable you some abilities to apply this in more accurate ways. Fusion 360's, angle adjustments are so easy to use, and there is actually some built-in ways to apply these forces in different ways. So if I select the second option in there, that angle delta, I can grab these and I can slide the arrow. I can move it one way or the other. That direction's not really doing much for me, but the other thing that's within this option is that I can limit the target. When I select that, what it does is it applies that force just to the area, the diameter that I pre-describe here. I can also click and drag on the center point there and slide this around. So one of the things I was playing with is I was trying to push down in the middle, and I was trying to set up one of those separation contact styles with one pushing down in the middle and two pulling up on the ends, and trying to see how kind of wacky I can get that to appear. I actually wasn't able to complete it because I was doing it very last minute, but this is a really nice way to adjust how loads are applied. So very quickly and easily you can limit the direction and location of that load. So what if you have a case where you want to apply the load in something that's not circular? Maybe it's a slot shape. In that case, you will use what are called split faces. So I want to apply this load in a slotted shape on the end of this face. To do that, I'm going to just insert a sketch onto that face. I'll select my sketch tool. I'll select to start the sketch, and I'll jump into using my slot tool, or I can use an ellipse. I can use a spline. It doesn't really matter. I'm going to select a center point slot. I'm going to use my visible origin, which I love. I'm so happy that we got that, to kind of locate the center of that slot, and then I'm going to click and drag and make this whatever size I want. So I did have a question. Isn't that just is the split just a sketch entity? No, it's not. At this point, the face, in terms of the simulation, is still that large rectangular face. In order to make it that smaller face to be able to select independently from the larger rectangular face, I use a command called split face. So we'll select split face. We'll select the face to split. And actually, I learned this in setting up this model. You can split multiple faces from multiple parts with this tool. So I actually split 5 different faces with that single line I drew across this in one single split face command. I was very enthused to learn that. If I wanted to, make this slotted shape on the back face here as well, I can go back to faces to split and select there. Once I click OK, now I have this face that I can use to apply the force to a very particular area of the model. So really important, don't always apply those forces over the entire face. Consider the forces that you're using, and whether it's being applied to multiple faces at once, and use things like split faces to gain more control over your simulations. Okay. Here's a quick rundown of the different contact types. I would definitely recommend that if you want to learn more and more about contact types, you select this shortcut in here, or you just go to the help and you search for contact types. It will get into all the different details related to that. Let's talk a little bit about some of the mesh settings. There are no limit of mesh settings that you saw there. I'm going to cover a number of them, but again, not all of them. As I mentioned before, we use solid tetrahedrons to represent these shapes that otherwise would be impossible to solve. We know how these tets actually react. That's how we actually do these finite element analyses. So within the mesh setting dialog, you will have all these different options, and I'm going to basically go through each one of these and kind of compare and contrast how they react. So turn angle effects, if you look at this slide right here, gives you an idea of what that's actually going to do. Essentially, when you have a very small angle, if you use a very fine angle there, it's gonna over mesh, let's say, some of the curved areas where there are angled elements coming in. I would typically, again, leave these as default unless you're having problems with your results, or if you're having problems with the display or quality, let's say, of your results. Adjacent mesh size adjacent mesh size ratio is really what I should say here. Plays with how fast or how slow mesh elements change from one to the next. So the model on the left has a very small number set, or the lower number set for it. And essentially, the elements are growing in that case from the very fine mesh control that I set on that internal face. They're growing very slowly to get to larger elements. That's what this is playing with, is the ratio of how quickly or how slowly mesh sizes change. If you use a larger option, it might look like this, which, is good in the sense that I might be able to run this faster. However, when you have elements that look like this, they typically give you problems, and we'll talk about that in just a moment. Creating curved mesh elements, that toggle that I showed you before, this really just increases the quality of the elements. It will typically have the same number of elements, but it basically puts nodes in mid edges to help capture the mesh or the curvature of the models that you're working on. So typically you want that on for, most definitely you want that on for final pass analyses. But if you're just trying to get results very quickly, this is one very quick way to simplify the mesh and get your results very fast. Use part-based mesh. This is pretty straightforward, right? If you select that toggle there, what it's going to do is it's going to adjust the mesh setting for the size of the part that you're working with. So one thing to note about this is that these are two different parts. I mean, this is obviously one big block, and this is some little rectangular block. With that off, it tries to just use kind of the same mesh size to capture all the geometry in this. If you turn that on, it looks at the size of that little rectangle, and it determines, this thing could probably give you some better results if it were to be meshed at a finer rate than the larger one. Aspect ratio, that comes into what I was showing you before with that growth ratio. Your tets can either be equilateral, like the one on the right. That is about the most perfect rectangle you could get. And that is a perfect aspect ratio, or it could be something like this, where there is a very long, there's like a sliver edge, and it causes this like sliver element. If you see a lot of those in your analysis, you might have your results affected by that. Getting all equilateral shaped tets is impossible, I'll say, unless you're working on a TET model. But it's generally you want to look out for elements like this. This is a very poor aspect ratio that can affect the quality of your analysis. Okay, let's see. I might not have time to do this, but no, I'm going to do it anyway. I don't care. So I do have another example in here. It's going back to that bracket. Like I said, I like it very much. It is the start one that you see here, and this is just using one of the advanced analyses types that we have inside of Fusion 360 to do basically what that challenge was trying to accomplish. It's going to try to optimize the design to reduce the weight considerably. So first things first, if you don't see the advanced analyses types in the selection, make sure to jump into your preferences, check your preview option here, and turn on your simulation advanced study types. And while you're here, I would highly recommend you turn on this guy. Live reviews are nice if you need to collaborate. The mesh workspace is also very nice. So, obviously I have all of mine on. I want to be using everything I can. But essentially, we have the same model. I mean, I actually kind of made it thicker and wider in areas because I wanted to give the shape optimization tool the ability to kind of, play with how this thing should really look in the end. I mean, the way that it was designed with all those odd angles might not be the best design. So, you could essentially make this like a big block with holes in it where the connection will be made, and then apply those different loads and the different settings and so on and so forth. So let's go ahead and run through the study. And again, I'm going to do this one much faster. I'm assuming that not everyone's going to be able to do this, and not everyone wants to solve this on the cloud. So, and I'm going to try to solve this while maybe we're talking about something else, but I'm going to select shape optimization. This is a very fun, very fantastic tool to use. We're going to check, the model setup. We're going to check the bodies. We're going to check the material. We'll get into our material properties here and make that the titanium alloy. And then we're going to define, I'll do 2 load cases here just to help demonstrate this, but we're going to define constraints and loads. So I'm going to hit C on my keyboard, and I'm going to fix the bolt locations, right? So 1, 2, 3, 4. I am not going to create that frictionless constraint on the bottom, and I'll talk about why that is maybe a little bit later. I'd like to show it, but I'm probably not going to have time to do it. But I'm going to apply those 4 constraints. I'll apply my load, and the load in this case will be applied to those 2 faces again, using the edge to define it. So this is going to be 8,000 pounds. And just like that, I've created 1 load case. However, there were 4 different load cases that we wanted to use to try to optimize this. So what I will do here is I will right-click the load case from the browser. I will clone that load case, and the reason why I'm doing this is because the next load is essentially very similar, but the constraints are definitely exactly the same. So I will go ahead and double-click on my load case 2 now and start to make the one change that's different here. It's going to be that the loads are going to be applied acting forward. So I'm going to edit the structural load. I will use a different edge to define the direction for this. And just like that, we've adjusted that. I think the value for this one is 8,500 or 9,000. I'm not really sure. We'll click OK. And from there, we can get into things like contacts again. We can get into mesh options, etc. But really what I want to do here is I want to look at other options within this tool, like preserve region. So obviously, we want to preserve certain areas. One thing to note is that anything that has loads applied to it or has constraints applied to it will be preserved automatically. I'm adding a little bit additional area here to preserve, only because I want to try to make sure that the connection point here isn't affected too much with this shape optimization I'm doing here. And that actually explains why I didn't do the frictionless on the bottom of this. Had I done the frictionless on the bottom of this, every shape optimization I would have done would have included like this very thin bottom surface. So that's why I chose not to do that in that case. From here, we can check our shape optimization criterion. This is telling us we want to make this, 30% the weight it is currently. That's very aggressive. I usually bump this up a little bit, 40, 60, 70. I mean, depending on how optimized something might be already, you can make adjustments here. If you go too low, it's possible it won't be able to solve or meet that optimization requirement that you set out. But here, I think I'm good. I'm going to go ahead and click solve. I'm going to select on cloud because I can only solve this one on cloud, and I'll select this guy here. I'll click solve study. Should happen very quickly. While that's happening, I might go look at something else because there are a lot of other different study types that we have access to. Okay, things like buckling, and the tower that you see here is something that I've included in the file set that you see. Essentially, you want to run a buckling study on any cases where you have thin members in compression. If you have thin members in compression, like a water tower or, a con rod or something like that, the thinness of that one could be a little bit questionable. Some of these images I don't fully endorse, but if you have thin members in compression, there's a possibility it will fail before it yields due to like static loading. So very important to recognize this behavior. If you ever have thin members in compression, I'd recommend that you do both a buckling study and a static study. Figure out which one is telling you whether or not it fails. Basically, at the end of it, if your buckling mode load factor that you see in this little dialog here is under 1, it's going to fail due to buckling. There's a good possibility it will fail due to buckling. If it's over that, it's telling you it needs to be 1.4 times this value in order to cause it to collapse, essentially. The load on that little water tower model that I used is like 3,000 pounds. So 3,000 times 1.433 is telling you what the value of that force would be to cause that buckling. And if you want to run through that, it's kind of cool. There's one feature in there that I suppressed that adds a second ring to help stabilize the model. The second time you run it, it will actually solve properly. Or I shouldn't say it'll solve properly, but it will withstand the forces. Thermal and thermal stress studies, pretty straightforward, right? If you want to dissipate heat, if you want to maintain some certain temperature, this is the tool for you. You will run a thermal study. If you're combining those with, static loads, forces, hydrostatic pressures, whatever it might be, then thermal stress is something that you definitely want to run. I mean, you can have thermal stress in cases where there's not like forces and pressures. I mean, it's caused by, heat expansion rates of different materials. I mean, you can have two materials next to each other. If one expands much faster than the other, you're going to have problems, right? So thermal and thermal stress, pretty straightforward. Frequency studies, there's a propeller that I included that you could run a frequency study on. Really easy to run. You actually don't even need to apply any loads, or you don't need to apply any constraints either. This will be used to figure out, resonant frequencies or mode shapes. If you do a frequency study and you have 126 modes at 0 hertz, that's caused by the free body movement. As I mentioned, you don't need to have a constraint. As you can see, there's no constraint in this study setup here. So that's just giving you the natural response of this shape that we're looking at. So you basically throw out the first 6. You can calculate as many modes as you want, but typically you're mostly interested in the first couple that give you real values. Obviously, 0 hertz doesn't do much for us. So that's what that will be related to. Very important to take note of that. And as I might have mentioned already, I mean, the each one of those 0 hertz modes, in this case with an unconstrained model, is related to the degree of freedom, so the XYZ and the rotational. So they will actually slide in the X, Y, slide in the Z, and then rotate about each one of those in the resultant animations that you can look at. So after that, you get into your nonlinear studies, and you can actually use nonlinear to solve, your linear static problems. What this enables is perhaps a little more insight into how things are being loaded and what's happening over the time domain, because at the end of a nonlinear study, you'll be able to look at the different time steps in the study solved. You'll also be able to use different material types and accurately represent them. You can use your hyperelastics, you can use your plastics, you can use your ductile materials that go beyond yield. You can use this to analyze cases where there might be changing context scenarios. To use nonlinear material types, make sure to check the nonlinear material library. There will be a number of different materials you can choose from here. If you select on one, it will actually use a curve to determine that. So here I've pulled out a real quick screenshot of one of these nonlinear materials, this aluminum moderate strength, and you can see the strain to stress ratio. So it's no longer using that elastic modulus to kind of simplify the aluminum behavior. It's using the true stress strain curve in this case. So Very, very important to note, and a very accurate way of solving studies. Event simulations are fantastic. I just saw one this morning of Mario jumping on a Goomba or whatever those things are called inside of Mario World. That's a very fun example of it in use, but there are definitely lots of real life scenarios where you want to use an event simulation. Anytime you have a load changing over time, either whether that be applied and then removed, an event simulation can do that for you. You can account for impacts, and that's what this curve is really representing in this slide that we're looking at. You can see that the 1,000-pound force is being applied over 1/1000th of a second, then removed. These results will enable you to visualize how the model dampens out that force or dampens out the effects of that inertial load. So really, really cool stuff. I hope the links work in the PDF that I provided of this this slideshow. There are 2 really great articles I'd recommend you read. Anyone looked at those yet? Let me know if those work. If not, I can share some other documents with you. Troubleshooting, as I mentioned, there's a lot of discussion on convergence versus divergence and why that's so important and why you want to use adaptive meshes to account for these things and to figure this out. Check out that singularity quick tip that I did. There's a really easy way of creating models that will have singularities. Anytime you apply a load to like a point, that will be a singularity. If you fix something by a vertex, it will be a singularity. If you have a sharp edge like we have in this case, in this bracket, that will cause a singularity. And what happens is the von Mises stress will continue to rise because what's happening is the elements are getting smaller and smaller in that corner. And essentially you're dividing by a smaller and smaller number, causing it to go to infinity. As mentioned, however, if your displacements converge, you can be very confident in your stress results. What you need to do, however, is you need to ignore the areas where those unreasonably high infinite value stresses are occurring. So essentially, if you get 1 or 2 elements away from where that singularity is occurring, your results are valid again. So using things like adjustments of the scale will help you filter that information. Using things like using the slider to get rid of all the high-end stuff will give you value as well. So is this bracket going to fail at this load? No, I don't really know the value of the load that I applied here, but there are real life designs where there's a sharp edge, and applying a 1 pound force and changing the mesh isn't going to affect how it reacts in real life. Obviously, it's still going to be able to withstand that. So at the end of the day, if your results are still wrong, check your setup. I can't tell you how many times I've had people swear that the software is wrong, that something's wrong with the solver, whatever it might be. Very few times are the issues related to anything with the mathematics. Very few times are the issues related to software, I'll say. The setup is where things can go wrong, right? Materials, make sure you're using the information that's provided to you by vendors. Double check your loads, double check your contacts, use different constraints, use additional parts, and use different contact styles. So, but at the end of the day, this is always going to be a numerical technique, and there will always be some discrepancy between this and real life exact values, if those even exist. So typically you aim for being within like 5% of what you'd really expect, or 10%, and using what you get from simulation, you can make changes to your models to get more and more information. Make sure to access your data through the web browser. It's a really quick way to share information. I'm going to actually jump back into Fusion. My my shape optimization should be done, and you can see it's giving me some idea of how I should optimize this model to both accommodate the loads but also reduce the weight considerably. So this is using that 40% mass ratio. You can use a slider and kind of visualize where unnecessary materials might be, anywhere there's that blue stuff. Looks like I missed a fixture, obviously. So double check your setup, right? That is a problem. Or maybe I didn't miss it. Maybe it just doesn't need it. Now it would still have it because, as I mentioned, anytime you have a constraint or load, it will preserve that region. So obviously I missed something there. If you do a shape optimization, at the end of it, you can select to promote it. It will take that mesh and will put it into the model. From there, you can start to change the design to actually, be manufacturable. Some of these shapes, unless you're using additive, are impossible to use. So make sure to consider the manufacturing process at the end of the day. I think that just about does it for me. I hope everyone learned something today. I'm always learning stuff when I'm preparing for these things. That split faces working across, different bodies, different components was something that I was pleasantly surprised for. I'm going to look through questions here. I'm going to answer them over the air. So if you have other questions, or if you want to, fire other questions to me privately, feel free to do so, and I will help you out. Other than that, have a great day, guys.